Page 322. And we're going to kind of pick and choose what we do here in this unit. We're not doing everything that's in Chapter 5, but the parts that we are doing in Chapter 5 are fairly significant. All right, now, we've practiced proving some theorems here recently. So one of our targets is we're going to prove the perpendicular bisector theorem. We're also going to use it. We're going to use the converse of the perpendicular bisector theorem. All right, we've talked about locus before. Locus is a set of points that meet a certain condition. Then we're going to do some more of that. We're going to we're going to use the angle bisector theorem and the converse of the angle bisector theorem. So there's quite a bit here in this one little section. Okay? All right, let's get started. Perpendicular bisectors. You learned before that a segment bisector is any segment, line, or plane that intersects a segment at its midpoint. If a bisector is also perpendicular to the segment, then it's called a perpendicular bisector. Now, we've used this term previously, even though the book just now defines it for us, but it makes perfect sense. Perpendicular bisector is a bisector that is perpendicular. Okay? We've even constructed this, haven't we? So, in the first picture here, PQ is a bisector, but not a perpendicular bisector. In the second picture, RS is a perpendicular bisector because it's both things. It's perpendicular to JK and it bisects JK. Now, one really nice thing about perpendicular bisectors, and this fits in with target number 3 here to talk about a locus. Well, first it tells us what a locus is again. A locus is a set of points that satisfies a particular condition. The perpendicular bisector of a segment is the locus of points in a plane equidistant from the end points of the segment. Okay? And we're going to prove that here in just a minute. But here's what they're talking about. If you've got segment AB, and you want to start picking points that are equidistant from A and B. For instance, that point, the distance from that point to A is equal to the distance from that point to B. So that point is equidistant from A and B. It's equidistant from the end points of the segment. So is that one. It's a different distance now, right? But the distance from that point to A equals the distance from that point to B. And that, and that, and that, and that, and that, and that. And guess what all those points would be on? They're all on the perpendicular bisector. If I constructed the perpendicular bisector, every one of those points would be on it. Okay? So that's what they mean here when they tell us that the locus of points in a plane equidistant from the endpoints of the segment is the perpendicular bisector. Does that make sense to you? Okay. Now, we're going to do something here to make our proofs just a bit easier. We know that the bisector of a segment goes through the midpoint of the segment. That's the definition of it. We also know that the midpoint divides the segment into 2 congruent segments. That's the definition of midpoint. So from now on, we will state that a segment bisector divides a segment into 2 congruent segments. So in other words, we're kind of making our own little postulate here. Okay? We're putting 2 things together in a logical manner, so we can do that. I mean, if we were writing a book, we'd have to actually spell it out, but I feel like this is spelling it out, I guess, really. So, from now on, in a proof, instead of saying that since so-and-so is a bisector, and then putting in a step to say that means, for instance, D is the midpoint, and then the next step we say the segments are congruent, we could skip the part saying, well, that means D is the midpoint. We could just go to saying that if segment whatever is a segment bisector, the next step we can conclude we get 2 congruent segments. All right? Saves us a step and a proof, but I'm not so concerned with a step and a proof as I am. I mean, we know this stuff. We might as well use it. Okay? And here is the perpendicular bisector theorem and its converse. If a point is on the perpendicular bisector of a segment, then it is equidistant from the endpoints of the segment. All right, I just made an example of that, right? So any point that's on the perpendicular bisector of a segment is equidistant from, in this case, A and B. The converse, if a point is equidistant from the endpoints, then it's on the perpendicular bisector. So if we know that E is equidistant from A and B, see how they noted that on the, see how they labeled that on the figure? By saying that that segment's congruent to that one, we know congruent segments have equal length. We know that length of a segment is the same thing as the distance between the endpoints of the segment. So it's all, hopefully all tying in together, things we've been talking about all year long. So since E is equidistant, it must be on the perpendicular bisector. Now, doesn't it make sense that if that's true, that that has to be true as well? Okay? Doesn't always work that way, but in this case, I can't even begin to imagine how it would both be true. Okay? So, we see the theorem. I think we maybe understand the theorem. Now we're going to prove the perpendicular bisector theorem. So, get ready to write this down. You're going to need to know this proof. So, the perpendicular bisector theorem says, if a point is on the perpendicular bisector of a segment, then it is equidistant from the endpoints of the segment. All right, so, that being the theorem, I drew a figure. I drew segment AB, and then I drew the perpendicular bisector of segment AB, and I called it CD. And then, so then what I want to prove is that any point that's on segment CD is equidistant from A and B. So, I get to decide what's given. So I'm given that segment CD is the perpendicular bisector of segment AB, and I'm given that E is a point on segment CD. So I need to draw E in it, don't I? And then look what I decided I needed to prove this theorem. If the length of EA equals the length of EB, that means E is equidistant, doesn't it? Okay? Because the length of a segment is the same thing as the distance between the 2 points. So if the distance from E to A equals the distance from E to B, then I've proven that E is equidistant from A and B, from the end points of the segment. So, look at what you've just put on your paper, the figure, what's given, what you have to prove. You need to see that what you're given is the hypothesis of the theorem, the if part. Hypothesis doesn't mean the same thing for us as it does in your science class. The hypothesis of a statement is the if part, the part that has to happen to cause something else to happen. Okay? So, our hypothesis is a point is on the perpendicular bisector of a segment. To get a point on the perpendicular bisector of a segment, I first needed a segment, AB, I needed its perpendicular bisector, CD, and then I needed a point on that perpendicular bisector, E. All right? So, I needed to know that segment CD is the perpendicular bisector of segment AB. I needed to know that E is on that perpendicular bisector. Then, the conclusion of our theorem is the part that comes after the word then. Then, all right, then what? It, meaning the point, is equidistant from the endpoints of the segment. So we have to prove that E is equidistant from A and B. And the way I'm going to prove E is equidistant from A and B is by stating that the length of EA, that means the distance between E and A, equals the length of EB. That means the distance between E and B. All right, so do you see how what we have If we can pull it off, we'll prove the perpendicular bisector theorem. All right. Now, let me get you started a little bit before I show you the plan, okay? So you know how to start. So we have all of our given in our proof. Now, what's this help us know? Since CD is a bisector of AB, I know, and we just spelled it out here, that we're going to skip what we used to have to put in. We used to would have to say D is the midpoint. Then we would say that the segments are congruent. So now we're going to say that since CD is a not that it's perpendicular, but that since segment CD is a bisector of segment AB, that segment AD is congruent to segment BD. And we'll call that our definition of segment bisector. So a slight revision to the definition of segment bisector. Okay? Now, what else do we know because segment CD, well, we use the fact that segment CD is a bisector of segment AB, but what else is segment CD to segment AB? It's perpendicular. And what does that mean? Well, if two lines are perpendicular, they form right angles. So we can conclude that angle EDA is a right angle and that angle EDB is a right angle. All right, now, if those are right angles, they're congruent. Now, I'm not going to change what I have labeled on my figure because, as far as I'm concerned, marking things as right angles is as good as marking them congruent. So angle EDA is congruent to angle EDB. All right. Y'all with me so far? All right, this is looking a lot like the steps we would put in to prove two triangles congruent, isn't it? We came up with right angles, then we stated that the right angles are congruent. We've got a pair of congruent segments in there, but, you know, we don't have triangles, so I guess we're doing something different. Kind of obvious that segment ED is congruent to itself. Is there any way I could prove that red triangle is congruent to that blue triangle? Yeah. Is that going to be helpful in any way? Some of y'all see where I'm going with this, don't you? Okay. Triangle EDA, the red one, is congruent to triangle EDB, the blue one. All right, those of you that think you know where I'm going with this, where am I going with this? Now I'm going to use the fact that corresponding parts of congruent triangles are congruent, aren't I? Because I can now state that segment EA is congruent to segment EB. The book would say CPCTC. I would say definition of congruent triangles. And that's really, really close to what we're supposed to prove. We're supposed to prove the length of EA equals the length of EB, and I've got segment EA is congruent to segment EB. If the two segments are congruent, what's that tell you about their lengths? They're the same. They are equal, aren't they? So, our last step is that the length of EA equals the length of EB, and the reason is because we know what congruent means. So, definition of congruent segments. And what do you think about that? You don't think about that? You ignore that? All right, so you need to know how to prove that theorem. Okay? All right, but we also need to know how to use it. So before we go on and start using this, remember what we know. We know that if a point's on the perpendicular bisector, it's equidistant from the endpoints. If a point is equidistant from the endpoints, it's on the perpendicular bisector. We know both of those things. Okay? Let's do a few from your assignment for today. So turn to page 327. And number one, they want us to find each measure. Well, for number one, it's the length of XW that they're after. All right? So look, and I know some of you already know the answer, but let's make sure that when it gets a little more complicated, we'll be able to figure this out. Here's what you need to be looking at. This segment, or this line, is perpendicular to segment WY, and since WZ is congruent to YZ, it must also bisect segment WY. So that's the perpendicular bisector of segment WY. Therefore, any point on that blue line is equidistant from W and Y. So if the distance from X to Y is 12, the distance from X to W has to be 12. And then look at number two. They want us to find the length of AC this time. Look what we have this time. We know that the distance from B to A is equal to the distance from B to C, don't we? And we know that segment BD is perpendicular to segment AC. So, since B is equidistant from the endpoints, doesn't that mean that B is on the perpendicular bisector of the segment? Yes, it does. So, if that's the perpendicular bisector of the segment, it's got to be perpendicular, and it's got to bisect. So that means the length of DC is 7. So then what's the length of AC? All right, on number 3, we have to find the length of LP, but before we can do that, we're going to need to find what X is. Is this one really as simple as it looks? Do I just set those two measures equal to each other? Yeah, I do. Because LN is the perpendicular bisector of segment MP, so the distance from L to P must equal the distance from L to M. So 10x minus 5 must equal 7x plus 1. Let's solve it for x. So we'd subtract 7x, get 3x minus 5 equals 1. Then we'll add 5, get 3x equals 6. So x equals 2. Now, LP is 10x minus 5. So 10 times 2 is 20, minus 5 is 15. All right, now, you've noticed this but I don't know if you've noticed it as much as you need to. What kind of triangle do we have in all three figures? It's actually an isosceles triangle, isn't it? Okay? Because two of the sides are congruent. I mean, think about it. When you use your perpendicular bisector to form a triangle, automatically you're getting legs that are congruent, aren't you? Because that x is equidistant from w and y. So you're getting isosceles triangles out of each of these. Remember what we talked about the other day? In an isosceles triangle, the altitude, remember what an altitude is? It starts at a vertex, is perpendicular to the opposite side. In an isosceles triangle, but every triangle has three altitudes, okay? In an isosceles triangle, unless we're stating otherwise, the one we're talking about is the one that goes from the vertex angle perpendicular to the base. So think about it. If the altitude is perpendicular to the base and it's on the perpendicular bisector, it bisects the base. So this is a statement I gave you the other day when we did coordinate proofs to help us out. And it's coming back into play again. Now we can actually prove why all of this is true. Okay? I can even prove that it bisects the vertex angle. If I go back to this, couldn't I use definition of congruent triangles again to prove that that angle is congruent to that one? Okay? So I can prove these three statements about an altitude from the vertex to the base of an isosceles triangle. So, working with perpendicular bisectors is the same thing as working with the altitude of an isosceles triangle. The altitude going from the vertex angle perpendicular to the base. With me? Now, that's the way it works in an isosceles triangle. But the perpendicular bisector of a side of a triangle does not necessarily pass through a vertex of the triangle. And in fact, if it's not isosceles or equilateral, it won't. So if it's not isosceles or equilateral, the perpendicular bisector of one side of a triangle will not pass through a vertex. Okay? For example, in triangle XYZ, the perpendicular bisector of segment XY does not pass through point Z. So, I put this on here. Don't assume that since it works out just perfectly for isosceles triangles that it does for all triangles. Because it doesn't. Okay? Now, something else you need to know, it's not really part of a learning target, but some words you need to understand. When three or more lines intersect at a common point, the lines are called concurrent lines. It's okay to call them intersecting lines, but when you call them concurrent lines, that gives everybody the idea that, hey, there's more than just two lines. There's three or more, okay? And, you know, you have a point of intersection. Well, now you would call that point where the lines all intersect the point of concurrency. Now, if you draw in all three perpendicular bisectors of a triangle, right? Triangle has three sides. Drawing the perpendicular bisector of each side, that gives you three of them. Turns out they are concurrent. They all meet at one point. You might not necessarily think they would, but they do. And that one point of concurrency is called the circumcenter of the triangle. So you might hear that word sometime. Might not. But anyway, it's where all of the perpendicular bisectors of a triangle intersect. All right, now, talking about a locus again. I'm shifting from perpendicular bisectors to angle bisectors. All right, we've talked about an angle bisector before. It divides an angle into two congruent angles. And the angle bisector can be a line, segment, ray, whatever. We're usually segments for us. That's good enough. Now, the bisector of an angle can be described as the locus of points in the interior of the angle equidistant from the sides of the angle. All right, now, so we've got angle ABC here. Ray BD is an angle bisector. What this statement's saying here, the locus of points in the interior of the angle equidistant from the sides of the angle. That means pick a point that's on that angle bisector. It's not equidistant from any certain points. It's equidistant from the sides. Remember how we measure the distance from a point to a line. We measure it with a perpendicular segment. Remember we drew those in one day, and we're all like, wow, this is easy. So, to get the distance from that red point to side BC,
Correction, Mr. Scott turned in. Please report to the manual for your lab at this time. Daily club and academic.
so I draw in that little segment. That's the distance from the red point to side BC. I draw in a perpendicular segment over here. That's the distance from the red point to side AB. Those two distances are equal. And it's going to be like the perpendicular bisector. It's going to be the theorem and its converse are both going to be true. If we know a point is equidistant from the sides of the angle, it's on the angle bisector. We know that if it's on the angle bisector, it's equidistant from the sides. We know both things. Okay? And here's how we state it. So these are our last two learning targets for today. The angle bisector theorem. If a point is on the bisector of an angle, then it is equidistant from the sides. So in this figure, that segment would have to be congruent to that segment. That would show equidistant from the sides. And if a point in the interior of an angle is equidistant from the sides, then it is on the angle bisector. So, if you know one, you know the other. Equidistant from the sides and being on the angle bisector, if one happens, they both happen. Okay? You think you're with me? All right, back to the assignment then. We're skipping 4. You don't even need to leave space for it. We're not going to do it. Number 5 then. On number 5, we see that ray BP is an angle bisector, isn't it? I can see that because I see that, if I can get that off of there, I see that these two angles are congruent, so the big angle got bisected. Since P is on the angle bisector, it's equidistant from the sides. If the distance from P to A is 8, the distance from P to C must be 8. Make sense? Well, maybe they'll get more difficult. Hope so, right? This time they want the measure of angle WYZ. So I'm going to outline angle WYZ. What's its measure? 23. Because that ray is the angle bisector. How do I know ray YW is the angle bisector? Because W is equidistant from the side. That's how I know that's the angle bisector. So if that's the angle bisector, if one half is 23, the other half is 23. How are you going to set up number 7? That's right. Because ray in Q is an angle bisector, therefore point Q is equidistant from the side. So let's see, that's 2 equals 2x a. I get 5 for x. Is that what you guys got? And then the length of QM would be 2 times 5 plus 2, so I'm getting 12. You getting 12? All right. Any questions? Then here you go. Page 323, do 1 through 3, 5 through 7, 9 through 14, 21 through 26, 39, You'll enjoy 39, 47, and 48. No, you won't? Yes, you will. It's an order. You will.